Okay, good morning, everyone. Okay, it's 9:30. Do you guys have any questions? If you have any questions, please put them on the chat so I can build up, have an idea what's going on. Okay. That's from the worksheet, Maggie? Yeah, all right. Any other questions? Please go ahead. Number 1 from the worksheet, sure. Okay. All right, so we're gonna do those, but before I start, answering those questions, I would like to make some comments about the quiz. Of course, you have the solution on Blackboard, and I try to send comments to everyone. So, but I would like to make a general comments about the stuff, the idea that a lot of you kind of messed up with. And for the range, you read the definitions. There isn't much I can say about that. But for number 3, a few comments about number 3. Okay. Please let me know if the writing is clear or not. If it's not, I'll try to fix it. Please be just say what's right or not. So let's do number 3 in the quiz. So T-linear, let me remind you that T-linear, it means that okay, T-linear means that T satisfies the 2 conditions of linearity. It means T of the sum is T of U plus T of V. And if you scale a vector and find its image, it's the same as finding the image and then scaling it. Now, there is a common mistake that showed up in your quiz, which is the following. Some student told me that the following issue. I gave you a function and I told you is it linear or not. So some students said they checked the value at 0 and they told me T of 0 equal to 0, then T is linear. And this is absolutely a false statement. If T takes 0 to 0, does not mean T linear by any stretch of the imagination. So part A, number 3, part A, I gave you the following function. Most of you were able to do this problem. There were no issue doing it, but this problem, which was 2 times absolute x1, and then the second entry was that x1 plus 3x2. Okay, that was the second entry. This one was not linear. You can look up the solution, but most of you got it right. T of 0 equal to 0, but still not linear. So even if T of 0 equals 0, doesn't mean it is linear. It could be linear or could be not linear. So telling me T of 0 equals 0, T linear is absolutely not a correct statement. What I said in class is the following. If T of 0 is not the 0 vector, then you can say not linear. That's about what we have. All right, so with this in mind, problem number B and C, which gives some of you a question, is the following. I will do C, and you guys look up number B on the solution. C was the following. I gave you T of x1, x2 to be equal to x1, 0. And the question was, is this function linear or is this transformation linear? And if so, give me the matrix A such that T of x equal A times x. The easiest way for us in this particular class to show that T is linear is to find the matrix that give us T of x equal A times x. And if we can write the transformation as a matrix times X, where A has constant entry, then automatically we can deduce it is linear. If we cannot do that, and then most likely it's not linear, and then we go and check where one of the property of linearity failed. So in this example, can we find the matrix A such that T of x1, x2 is A times X? Can we do that? Now, I got a lot of answers, and I have some student who wrote, if my memory is right, A equal 1, 0. Is this possible? Is this possible? I'm asking you the question.
No.
Is it? No. A lot of you did that. This is absolutely impossible to happen because if A is 1, 0, multiplication makes no sense whatsoever. Absolutely no sense of whatsoever. So what should be the size of the matrix A, which will allow us to write it if we can? So a lot of you wrote this, and this is absolute. So what should be A so that when I multiply it by x1, x2, I get the vector x1, 0? First, what should be the size of A? Exactly, it has to be 2 by 2. Exactly, it has to be 2 by 2. And what should be A? 1, 0, 0, 0. If I take this matrix A multiplied by that, it gives me x1, 0, 0, 0. So T, this transformation T is given by a very nice rule. It takes a vector x and it multiplies it by the matrix A times x. This automatically, because of matrix multiplication, it will satisfy both conditions. So that was the issue that you had with number T. Another question before I move on to your question is the following. Let us say a student did that. He want to show me that it is linear and tell me if the student is right or wrong. So the student tell me, okay, I want to show you it is linear. So I will take up the same function, T of x1, x1, 0. And the student to write the following. T is linear because take C equal to 2 and x to be, let us say, 2, 1. Then T of Cx for this particular is C of Tx. So the student computed 2 times the vector, he got 4, 2. And he computed T of 4, 2. Then the student computed 2 times T of 4, 2. And then tell me that this is linear. Is this an acceptable, mathematically acceptable answer? What do you think? No, because. Why it's not an acceptable answer mathematically? Alex is absolutely correct. Why I will not accept that? What is the mistake the student did? Unmute yourself and please express yourself because I don't want you to repeat the same mistake more than once.
Is it that a value was given for x2?
What?
Is it that a value was given for x2?
What do you mean? I
Well,
think it's correct, but I'm trying to push a little bit to make sure and everybody understand what you said.
well, x1 is the only component that's a variable. The other one has to be 0 by default.
Yeah. So why this approach is not a correct approach? Why, if the student will write this and tell me it is linear, I tell that's not really a correct argument.
Just because it holds true for one C doesn't mean it holds true for all C.
Exactly, because if it's true for one C and one particular vector does not make it true for every C and for every vector. So it may be true for that, but why, if it's true for C equal to 2, it's true for C equal to 5 or for C equal -2. So if it's true for one example, does not imply it's true for every other example. So that's why this argument will not carry. Because to show linear, you have to show that this holds regardless what C and X is. And also you have to show that the addition holds for every two vectors. So if you prove it to show for one particular vector, I will totally disagree. I said no, to be linear, it should hold for everyone. However, if you want to show not linear, it's enough to give me an example. So that's really the idea. So if you tell me one vector, I tell you no, it does not imply linear. So for us, the easiest way to make sure it's linearity is actually to come up with this matrix A, which give me T of X equal A times X. That's really the easiest way as far as we are concerned in this class. All right, so this is not about the quiz. Please go over your mistake. I tried to put comments, and I did put the solution on Blackboard. So now I'm gonna go back to the questions you asked, and from the worksheet. And the first question was the following. Okay, I'll use a clean piece of paper. All right. So the goal of this problem is to review why, if the transformation is linear, then T of X equal A times X. So the last thing I did in class last time, not the last thing, the main idea I did in class last time was the following. I told you that if you have a transformation T, let us say it doesn't matter from where to where, and it is linear. It means, you know, that it's like rotation. Rotation, I told you it's linear geometrically. So if you have two vectors and you rotate them, their sum will go to the sum of the rotation. So geometrically, it's a linear transformation. So what this theorem tells me, if you know it's linear, you know, that geometrically or somebody told you, then automatically you can write T as A times X. So if it is, once you know it's linear, then it's automatically given by a matrix. And in class, I told you, or we proved that the matrix is what T does to E1, what T does to the unit vector E1, unit vector E2, etc., unit vectors all the way up. Now, in this problem, I actually am trying again to convince you of this the case. So I actually want you to make sure you understand this idea. So I gave you, let T be, so I gave you a transformation T, which is linear. And I gave it from R2 to R2 because it doesn't matter. They're all easy to work with. And I told you, so this is linear. And I told you T does the following. It takes the vector E1. We never have to forget what E1 and E2 are. E1 and E2 are, E1 is the unit vector, that's E1. And E2 is the unit vector here. Okay, so I tell you that it takes the vector E1 to the following, 5, 1. And it takes the vector E2 to the following 5, 6. Okay, so that's what it does. And so I know it's linear. It means it has this nice property. And I only know what it does to E1 and E2. So I only know what it does to two vectors. Now the question is, do I know what it does to any other vectors? So with so little info, I can actually figure out a lot of ideas. So I'm guiding you through that. We did it in class, but I want you to actually understand it better. What's the idea? I told you, first question, write x1, x2 as a linear combination of E1 and E2. So write any vector x1, x2 as a linear combination of E1 and E2. Oh, sorry. Sorry, it's from R3. My apology. It's from R3. T of R3. My apology here. So it's from R3. I didn't read it carefully. So it takes E1 to 5, 1. It takes E3 to 5, 6. And it takes E1, E2 to minus 1, 1. Okay, so I know where E1 go, the unit vector, so I know where this one go. I know what happened to E2, and I know what happened to E3. So now I want to figure out what happened to every vector x1, x2, x3. So I take any vector, x1, x2, and x3. And my first question is, write it as a combination of E1, E2, and E3. As a linear combination. It means I want to write it as something times that, that's a linear combination, plus something times E2, plus something times E3. That's what it means in linear combination. So what are the natural weight? x1, x2, x3. So that was my first question. Every vector could be written as a combination of E1, E2, and E3. And you guys, as I said, you've seen that definitely in 261, in Calculus 3, that's the I, the J, and the K vector. We call them E1, E2, and E3. And every vector could be written x1i, x2j, x3k. That's really what we are doing, but we give them another name. So that's xe1, x2, e2, x3, e3. And now I want you to use part B is find t of x. So now with this in mind, can I find t of any vector? So if I know what is t of any vector, now I'm going to use the linearity. It means t of x1 e1 plus x2 e2 plus x3 e3. Now linearity tells me you can break the sum. It means t of x1 e1 plus t of x2 e2 plus t of x3 e3. We can totally break the sum. Linearity tells me that you can take the scalar out as well. So that's going to give me x1 t of e1 plus x2 t of e2 plus finally x3 t of e3. Now I know t of e1, I know t of e2, and I know t of e3. So if I know the vector x, it means I know its component, I can actually compute where t will send the vector x2. So this is going to be written as x1. Now t of e1 is 5, 1 plus x2, t of e2 is minus 1, 1 plus x3, t of e3 was 5, 6. So it means I can rewrite this as the following. This is x1, x2, and x3. That's 5, 1, minus 1, 1, and 5, 6. And that's the matrix A that we're talking about. So the matrix A has for column, the first column is what T does to E1. The second column, what T does to E2. And finally, what T does to the vector E3. So in other words, if I know what the transformation does only to the unit vector, and I know it's linear, I know what happened to every vector. And this matrix A, you remember we gave it a name, and this is what we call the standard matrix of T. And we denote it by T with bracket, which means the standard matrix. All right, any questions about this problem? So now let me look at the same problem, not the same problem, again, the worksheet. I will look at number 3. And we have the following problem. I look at part A. Is the following. We have the following function, f from R to R. And given by, so that's the old simple function, which is given by f of x equal 3x. I know everybody knows how to do this problem. I'm not. And g is given by g of x equal 5x. Those are the two functions. And now I'm actually asking you to find a formula for f of g of x. What do we call f of g of x? What does f of g of x mean? you guys remember what I'm asking you to compute? The composition of two functions. So basically, I have two functions f and g. The first one take x to 5 times x. The second takes x to 3x. Now the composition does what? F of g of x is f of 5 times x, because that's what g does. It multiplies a number by 5. F will multiply it by 3. So it's 3 times 5x. It means 3 times 5 times x, or it is 15x. Okay? So this is just a composition. So we have two functions. We have g takes effect x to 5x, and then we have f. And what I'm asking you is, if I can go from here to here, what's really the composition does? Now, the idea here is practice this with, with transformation. So my question is, suppose A and B are 2 by 2 matrices, and we have T from R2 to R2. And it's given by the rule A times X, typical matrix transformation. And then I have another one, F, from R2 to R2. And it's given by B times X. So those are the true transformation. And now I'm basically looking at the following transformation, F of T of X. So what am I really looking at? So I have, this is R2, R2, R2. I have T and F. T takes a vector X to something, and F take a vector X to something. I'm actually looking at the transformation from here to here. I'm telling you what's the rule for this transformation. What's really the rule of this transformation? Okay, the idea is just, I gave the first one because this is really the same, but in a more general context. That's really what it is. So what's f of t of x? It means f of t. What does t do? To a vector. Multiplies it by a vector x. What does f do? What does f do? This is now the input of f. It takes, it's b times a times x. It means it's b times a times x. And that's the rule for f of t of x. So if A is a matrix for t and B is a matrix for f, what this is telling me is that when I take the composition, the matrix for the composition, so this is really the composition, is B times A. So you multiply the matrices. So if I know A is the matrix for T and F is the matrix for B, then the matrix for the composition is actually the product of the two matrices. That's really what B is really about. Okay. Any other questions? Right. Before we move on to basically a different topics, and I would like to make sure that you guys have a good understanding for the standard matrix. So we know where it comes from, but I want to make sure that you guys can find it. So I will just do very briefly 2 problems and then I will proceed. So problem number 1 from the book is fairly simple, but just to make sure that you guys can do that. So if problem number 2, I have T of E1 is T of E2, and it's a bunch of numbers, 3, 1, 3, 1, and this is minus 5, 2, 0, 0. And the question was the standard matrix of T. So the standard matrix is always what T does to E1, what T does to E2. So this is 3, 1, 3, 1, minus 5, 2, 0, 0. And what does this mean to you? It means to you that if I take any vector x, what t does to this vector is it takes the standard matrix and it multiplied by it. That's what this means to us. Okay, right? I look at one more and then I will move on. So let me pick another problem, like the problem we did on the board, the last problem I did last time. So I don't know which one is in the book. Suppose I take the following problem, which is something along number 7. Okay. And the problem number 7 is actually, it does two things. I have t from R2 to R2, and it does the following. It rotates through minus 3 pi over 4, and then reflect. Then deflect across the x1 axis. And the question is, find the standard matrix of t. Right, we're going to look at that and then we proceed. So finding the standard matrix, basically it means I need to basically find what t does to the unit vector e1 and what t does to the unit vector e2. So we read what's happening. What does my transformation do? I'm going to leave an empty spot here. I will come back to it. It takes a vector e1, and then, so what it does to e1? It takes e1, rotated by minus 3 pi over 4. So rotating it, if I rotate a vector and I want to know where the vector goes, so that rotate minus 3 pi over 4. So the picture is here. That's my picture. That's my vector 1, 0. I'm going to rotate it minus 3 pi over 4. So this is going to end up here. And then after that, I'm going to reflect it through the x1 axis. So it's going to end up right here. So that's really my t of E1 geometry. And the question is, what's this vector? We can sometimes just look at it and figure it out because these are easy angles, or we can do it without looking. So to be able to do it without looking, I need the rotation matrix. Now, minus 3 pi over 4, what's going to be the rotation matrix? If you rotate by minus 3 pi over 4, the rotation is going to be the cosine of minus 3 pi over 4. The cosine of minus 3 pi over 4 is going to be minus the square root of 2 over 2. Sine of minus 3 pi over 4 minus the sine and the cosine. So you can either look at the picture and figure out this vector just geometrically or using trigonometry. So we know what's going to be minus square root of 2 square root of 2, or we can multiply it by the rotation in case we forget what to do. I multiply by the rotation, it's going to give me minus square root of 2 minus square root of 2. So I rotate. And then I reflect across the x1 axis. So if I reflect across the x1 axis, what will happen? All right, the x component will not move. The other component, it becomes plus the square root of 2 over 2. It means t of E1 here is minus square root of 2 over 2 and the square root of 2 over 2. So I know what happened to E1. I do the same to E2. I rotate, and then I reflect. And we follow what happens. So the picture for E2 is going to be like this. So I'm going to be exactly the same. I will not do all the details. So this is my E2, right here. I'm going to rotate it minus 3 pi over 4, which is going to land me here. And then I'm going to reflect it, which is going to land me right there. So that's T of E2. Now I can repeat verbatim what I did before, and I'm gonna get square root of 2 over 2, square root of 2 over 2, because the picture is not hard. So now what's gonna be, so this is my T of E2, and I already find T of E1, and now I can basically find the standard matrix. So the standard matrix is going to be T of E1, T of E2. So it's going to be T of E1 minus the square root of 2 over 2, the square root of 2 over 2, and this is going to be square root of 2 over 2, square root of 2 over 2. And now if I take any vector, regardless what vector is, any vector I want, if I rotate it by minus 3 pi over 4, and then I reflect it, I know exactly what happened to it. I just take the standard matrix, multiply it by it, and I know where everything happened to it. Right? Okay, any other questions before I proceed to the new material? All right, so today we're going to move on to section 2.8 in the book. So we're done with linear transformation, and we're going to talk about very new idea, notion of subspaces. If we know the angle after the reflection, is it okay to just use that angle? But you have to be very careful. Yes, you can do that, but make sure you don't do it wrong. Sometimes you do those, yeah, in this particular problem, you're right. But if I give you, which I probably will assign as a homework for next time, if I give you, I'm answering Alex's question, is I give you a rotation followed by reflection across the line x1 equal x2, for example, then finding the angle becomes hard. Okay, so I will give you this problem as a homework for next time, and I let you think about it. Okay, so today we're going to move to a new idea called subspaces, section 2.8, and basis of a subspace. Those two sections are a little bit abstract in nature, but they are based at the heart of the course. So we're going to start talking about subspaces. And before I give you the definition, some terminology I will use, and then we read the definition. Not terminology, it's a small example. Suppose, so subspaces 2.8. Okay. Suppose I tell H is all vectors x1, x2. Suppose x1, x2 in R2. To satisfy the condition, the first component positive and the second component positive. So let H be all the vector in R2. So H for me, of course, R2 is, for us R2 is all ordered pair. All of them. That's R2. H is not, of course, all of R2. Specific vector in R2. Specific vector that satisfies the first component is positive and the second component is positive. So that's H. And if I want to visualize H, how can I visualize H? Quickly. How can I visualize H? Quickly, I want answers.
Belonging to the first quadrant.
What? Repeat. How can I visualize H?
It would be the first quadrant.
It will be the first quadrant, all of it. That's what H is. That's how we're going to visualize it. Because what's my H? Every pair of numbers, every ordered pair of numbers that has the property the first component is positive and the second component is positive. So that's really H. So it's what we call a subset of R2. Not all of R2, very particular ordered pair. The first and the second component are positive. So the way we're going to visualize it, that H is every vector such that its first and second component is positive. Those are the vector in H, everything here in H. So in this section, we're going to talk a lot about collection of vectors or based in R2 or collection of vectors in R3. So this is what I mean by collection of vectors. So we start with a definition of subspaces and we're gonna work with that. today. So definition. Let H be a collection of vectors in Rn. That's exactly here what I'm talking about. When I say collection of vectors, I wanted to start to have a picture. It means bunch of vectors that have a very specific properties within R2 or within R3 or within R4 and so on and so forth. We say that H, it means this collection of vectors, is closed under vector addition if whenever two vectors are in H, if I pick any two vectors in H, and I add them, their sum is also in H. So we say it's closed under vector addition if you take two vectors that are in this collection H, you add them. If the resulting vector, the new vector, is in H, we say that it's closed under addition. We say that it's closed under multiplication if you start with a vector belong to this collection, you scale it. If this new vector also in H, regardless what the scalar is, we say that it's closed under scalar multiplication. What does it mean to say that H is a subspace? We say that H is a subspace if it has satisfied three conditions, not one, three. 0 has to be one of the vectors. H has to be closed under vector addition. It means if you start with any two vectors, you add them. The new one has to be also one of the vectors in your collection. The third, it has to be closed under scalar multiplication. You start with a vector in your collection, you scale it, you get a new vector. Is this vector in your collection? If it is, regardless what the scalar C, and then we say it's closed under scalar multiplication. So subspaces are specific collection of vector within R2 or R3 that has to satisfy all the three conditions. And today we're going actually to basically study this. So we're going to start with the first example I picked. And my question is basically, is it a subspace? So we're going to look at every aspect of it. So now, okay, here we are. So my first example is, suppose H consists of all vector x1, x2 in R2. So my vectors are in R2 here because they have two components. And they satisfy the following properties. The first component is positive, and the second component is positive. And my question is this a subspace? It means, does it satisfy all the three conditions of a subspace? All right, let's start with the first one. Is the 0 vector in H? Yes or no? So the 0 vector is 0, 0. Is this one of those vectors? Does it satisfy the condition x1, x2 positive?
Yes.
Of course. So 0 is in H. My question 2 is H closed under vector addition? What does this mean? It means that if I take two vectors that satisfy this condition, any two, arbitrarily, I add them, I'm going to have a new vector. Will this new vector satisfy the same condition? First, we're going to do it geometrically to build your idea, but I will usually prove it algebraically so we can practice this. So geometrically, what I am talking about, and I need a paper. Okay. Geometrically, I'm talking about that. So this is, in this particular problem, geometrically, we can visualize H as every vector where the tip of it lies in here. Every vector whose tip absolutely lies in here because the vector has to satisfy both entries are positive. So if I take two vectors here, arbitrary vectors, two vectors, and I add them, of course, I'm going to create a third vector. So I have a new vector now. So I'm going to add them geometrically. So this is my x, This is my y. I'm going to add them. That's my new vector, x plus y. And geometrically speaking, is this new vector also in H? What everybody say?
Yeah.
Absolutely, yes. So geometrically is actually very clear. But now how can we do it algebraically? Because sometimes, you know, if I'm in R3, my geometry actually is not great. In R4, I'm out of it. So the question is, can I show those, how can I algebraically show that, yeah, this is really in H? And this is a little bit new to you, but it's not hard. So how do you show that algebraically? Okay. So, and the question is, yes, here we will verify it algebraically. So how do we do that? Okay, algebraically, it means we start with two vectors in H. So let x and y be in H. What does it mean, H? It means my vectors have the property that the first is positive component, the second is positive. My y has the property, the first is positive and the second is positive. So I have basically those two vectors, where entry is positive. Now I'm going to add them. And then we're going to look at their sum. I'm going to add them and check, is the new vector x plus y have the same property, but algebraically. So I add them, I get x plus y, x1 plus x2, y1 plus y2. Will this new vector have the property that the vectors in H have? It means, will its first component be positive and the second component be positive? What do you think?
Yes.
Because, and now I want the algebra.
If both the x's and both the y's are greater than 0, then the sum of two things greater than 0 will also be greater than 0.
I'm done. We're done. So now, because initially x1, x is in H, it means I'm starting with a vector x where, sorry, x1 plus y1. And this is x2 plus y2. Okay, I'm starting with a vector x where the x1 is positive, x2 positive, y1 positive, y2 positive. So now when I'm going to add them, so we know that this happening, it means x1 plus y1 is positive, and also x2 plus y2 is positive. Since both components are positive, it means my new vector is in H. So that's how we're going to verify those algebraic. So now question number 2 is, so it's closed. So H has the two properties, 0 is in H, and also closed under addition. Now question number 2 is H closed under scalar multiplication? It means if I start with a vector in H, this is my H. I start with a vector in it. So this is my vector. And I scale it. Again, geometry for now. Will this new vector be also in H?
Not for every scalar.
Okay. All right. Do you agree with him? Not for every scalar? Absolutely. Because once you take the scalar as negative, your new vector is absolutely not in H. And so if C is equal, yeah, you're absolutely correct. If C is positive, yes, but the scalar C has to take any value. There is no restriction on C. So C could be negative, and because of that, we can, if I take C to be negative, my new vector will not be in my space H. So geometrically, it seems to be definitely false. So now we go back to, how do you guys have to show it? You give me example. Is H closed under scalar multiplication? You just give me example of a vector in H. So we have to start with the vector in H. So let x be equal to 1. X is absolutely in H. That's what you have to start with, because both components are positive. And take C equal minus 1. So you take C times X, you're definitely getting minus 2, which is not in H. So is H closed under scalar multiplication? And the answer is no. Therefore, is H is a subspace that's not a subspace because scalar multiplication failed. All right. Example number 2, try not to look at your notes. And I want you to give me an example of a collection of vectors within R2, which is closed under scalar multiplication. It means you take a vector and you stretch it, you remain within the space, but fails vector addition. It means you add 2 vectors, the resulting one will not be in your space. Can anybody give me an example? I'll give you 2 minutes to think about it. So I want something which is closed under multiplication, scalar multiplication, not closed under vector addition. Scalar vector, you stay within your collection, but add them, you can leave. Okay, I'm giving you a minute to think through that. Okay, and whoever find an idea, please say it in words because you cannot sketch.
I think an example would be where you would have HB where the 2 quadrants are like opposite of each other. So if you had it like H was quadrants 1 and 3 or 2 and 4.
Okay, so let me stick to 1 and 3, and then I will define it for you algebraically. So your classmate, okay, I don't want to waste too many papers. I have an empty spot here. So this is the idea of your classmate. Take H to be every vector that can land either here or here. And before I do everything algebraically, with this H, it means all the vectors such that the tip is right here, be closed under scalar multiplication. So geometrically it is, because you take a vector here and you scale it, you're gonna end up here. So it's gonna be closed under scalar multiplication. However, if you take a vector down here and you take this one here and you add them, the resulting vector does not have to be in H. So that's the geometry of the picture. Now the algebra. First, how can I algebraically describe quarter 1 and quarter 3? So I'm not going to tell you X is in quarter 1, quarter 3. I'm going to give you a algebraic way of describing those. Anybody can describe those vector algebraically?
It's when both x1, x2 are greater than or equal to 0, or when both x1, x2 are less than or equal to 0.
Okay, so either both positive or both negative. Is this a good description?
Yes, we have to specify that both coordinates have to be the same, positive or negative. It can't be like one positive, one negative.
Exactly. Now we're gonna a little bit, both of you are correct, but I'm gonna a little bit refine it. So I'm gonna define it to be all x1, x2 such that if I multiply the coordinate, what should I get?
Positive number.
Positive number. Will this characterize what you are talking about?
Yeah.
Because how can both the product be positive if both are positive or if both are negative? So that's how I'm going to characterize the quadrant algebraically. And that's exactly my example in here. So example number 2 was H all vector x1, x2 such that x1 times x2 is positive. And now, is H closed under scalar multiplication? And geometrically, yes. If you start with a vector x and you scale it, if the scalar is positive, suppose you start with a vector in the first quadrant. If the scalar is positive, you stay in the first quadrant. If the scalar is negative, you're going to go to the third quadrant, but either way, you're going to stay in H. So geometrically, it's clear But now I want to work on it algebraically because I want you to handle those problems algebraically. So what does algebraically mean? You start with a vector in H. It means that, what does it mean in H? What characterizes those? It means the product of their component is positive. And let's see, be any scalar. And I take C times X. We look at C times X and we check if this new vector, Cx, is in H. So what is Cx? It's Cx1, Cx2. Is this vector in H? But what does it mean to be in H? What does it mean to us to be in H? How can I convince you something in H? By showing you that the first component of your new vector times the second component is positive. That's what is the property of it. So now this new vector, will this satisfy the condition that its first component multiplied by its second component is positive? Let's see. I took the first component multiplied by the second. Is this a positive number? And why? Okay. Let's multiply them. This is Cx1. So I'm multiplying them to basically sum Cx2. If I multiply them, I get C times C squared, x1, x2. Is this a positive number? Regardless what x1 and x2 is, as long as x1 and x2 positive, what can we say here? Is this a positive number? C squared is positive. What about x1, x2? Is this positive?
Yes.
Because why x1, x2 positive? I want an answer. Anybody, Mikey, Alex, all of you, just why x1, x2 is positive? We defined it that way, exactly, because x1 and x2 are not anything in R2. They are not arbitrarily vector in R2. They are specific one. So my vector x, my starting vector x is in H. It means that my starting vector cannot be minus 2, 1. Because this is not in H. My starting vector has the property that the product of its component is positive. So this is positive because my initial vector is in H. So the resulting one is positive. So that's how we handle those problems algebraically. All right, so my second question was, what you expect is H closed under vector additions. And I want an example. I drew the picture. I want an example. Is H closed under vector addition? It means if I take two vectors in H and I add them, okay, will I end up in H? Okay, who can give me example? I gave you one on your worksheet, on the lecture note. Who can think of another example? Okay, I'm expecting answers. So it means my H is those. And geometrically, it seems that scalar multiplication, vector addition fail. I want two vectors, x and y. I want both in H. I want this in H. But when you add them, the new vector does not satisfy the property of H. All right, so who's ready? Not the one I gave. Don't look at my notes for a second. Who's ready? Quick, I have a lot of examples to cover.
Use the vectors 2, 1, and -1, -2.
2, 1. So 2, 1. And what do you want here?
-1, -2.
-1, -2. Both are in H, so our starting point is correct. I add them, I get 2 minus 1, it's 1. I add them, -1, not in H. And the vectors were 2, 1, and -1, -2, right there. I'm adding them, I'm leaving H. So H is not a subspace. But before I move on to my third and fourth example, I would like to make a note. Let us say that we didn't see examples and we didn't know whether it's closed or not. And we tried to show it algebraically. Where will our algebraic approach fail? So I start with two vectors, x1, y1, and I start with another, I need a black pen, x2, y2. Sorry, I need a nice paper. Okay, so let us say we didn't see it geometrically, and we're thinking about this really algebraically. Where will things fail? So suppose I start with x, x1, x2, and my y, y1, y2. And this is in H. It means the product is positive. So I'm starting here, and I'm starting here. And I add them. But I was not careful why I add them. So I'm going to get x1 plus y1, x2 plus y2. And you have to tell me where things will fall apart. And my question is this in H? And I didn't see it geometrically, so I'm working algebraically. What does this mean? To be able to see if this is in H, I have to take the first component times the second. And I ask myself, is this positive? All right, so, okay, I don't know. I know x1, x2 positive, y1, y2 positive, but I have no idea about this product. So I multiply out just to make my things a little bit easier. I get x1 plus x2 plus x1, y2 plus y1, x2 plus y1, y2. And now I should start seeing the problem. I know that this is positive. And I know that this is positive. But is there any reason that this term is positive? There is no reason. x1, x2 positive, y1, y2 positive, but then I'm going to run into a problem right here and ask myself, is this term positive? There is nothing which tells me is this term positive. And this will give me a clue whether there is a problem or not. So I tried to satisfy the property. I basically couldn't do it very easily. I have those positive, but this I have no clue why this is positive. And this will start showing me that there is really an issue, that I can construct vectors such that this term actually make me break the rule. So if you do it algebraically, that's where you're gonna get into trouble. All right, so now I gave you two examples. Both of them are not subspaces. The first one failed to be subspace because it was not closed under scalar multiplication. The second was not a subspace because it failed to be closed under vector addition. So now I need to give you an example of a subspace. So I want to give you an example of something which is have the zero vector, closed under addition and multiplication. Who can think of an example? So I want something so that if I take the vector, stretch it, I don't leave my subspace. So this have to already give you a picture of what we want. And then we add two vectors, we don't leave them. So who can think of something geometrically that may satisfy those two conditions before I do it algebraically? Ideas? Anybody? Anybody can think of anything that, you know, when you take a vector and regardless how to stretch the vector, so it has to have the zero vector in it. And whenever something in it, as long as we stretch it, will remain in it. Any picture?
The only thing that comes to mind is something that would include like just everything on that graph.
Everything
Like
on that graph, it means all of R2.
Yeah.
Okay, that's a very good approach. I want another one. Otherwise, I wouldn't be talking about subspaces.
Yeah, I know. That's the only thing that came to mind so far.
Anybody else? So absolutely that. I will mention it at the end of the lecture. I have to. Anybody else?
Would a line also be included?
A line. A line. Be precise about your line. Any line or specific lines?
You would have to go through the
A
origin.
line through the origin.
A line through the origin. Absolutely correct. A line through the origin. And then we're going to do that algebraically. That's a line through the origin. Okay, this is a subspace. And you guys are struggling because there is a reason for your struggle, because actually we're not going to find a lot of them. But line through the origin is absolutely a subspace. Okay, if I take a vector here, regardless how I stretch it, I will not leave my line. If I take two vectors, regardless where I take them, and I'm going to add them, definitely I will stay in H. So line through the origin are absolutely subspaces. So that's the geometry of the line. And now I'm going to move to the algebra of the line and how I'm convincing you that algebraically it is correct. Geometrically is actually fairly clear. So I'm giving you the following example. So I will elaborate by that. So I took H to be a line. So through the origin. So I took H to be, so suppose the equation of this line is x1 plus 2x2 equal to 0. So I took H to be all the vector x1, x2 that satisfy this condition. That's my H. And I asked you to do the following, show that this is a subspace. So go back to my notes. Right there. Sorry, I'm missing a page. Right here. Okay. So this is my example number 3. Let H be the collection of all vector x1, x2, such that x1 plus 2x2 equal to 0. And this is basically equation of a line. It means that the point x1, x2 is a point on this line. My first vector is just to familiarize you, just to push you a little bit. Give me example of 5 different vectors in H. So, okay, you guys give me vectors in H. It means you have to give me vector that satisfy this condition. Like, who can give me one vector at least? Please be quick.
2, -1.
2, -1. Is he correct? So if I put 2, -1, does it satisfy this condition? 2 minus 2 equal to 0. Yes, this is in H. And there are tons of them, of course. 4 minus 2. 4 minus 4 equal to 0. And if I sit down and start sketching all those vectors, we know that those vectors are like this. One is a scalar multiple. All the vectors are like that. So these are a bunch of examples. Now question number 1 is H a subspace. We need to show that H satisfies all the 3 properties of the subspace. So we have to show that it satisfies all the 3 properties. And if one fails, either 0 not in H, or scalar multiplication fail, or vector addition fail, if one fail, that H is not a subspace. So we're going to check every one of them. First, the 0 vector. Of course, it's in H, because 0 plus 2 times 0 is 0. As simple as that. Close under vector addition. How do we prove that? Algebraic. Geometrically, we saw it. So I take a vector x, x1, x2, and another vector in H. Immediately, those vectors are very particular ones. Those are not just any vector in R2. Those are vectors that have the property. The first component plus 2 times the second is 0. So I'm thinking about 2 minus 1. I'm thinking about 4 minus 2. And the second one have the property, the first plus twice the second equal to 0. So I have very, very particular vector here. And we need to check if their sum is in H. It means We take those two vectors, we add them, we create a third vector. The components are x1 plus y1, x2 plus y2. So that's my new vector. And now my question is, does this new vector satisfy the properties that the vectors in H have? It means if I take the first component and I add to it twice the second, will I get 0? That's what it means to be in H. Will this new vector satisfy the properties that vectors in H have? And that's verbatim what I did. So I took x1 plus y1 plus 2 times the second component. And I asked myself, can I convince you that this new vector satisfies? Okay, so I'll write it a little bit big here so you guys understand. So I took, I'm killing so many trees. So x1 plus y1 plus 2 times x2 plus y2. And my question is this equal to 0? Knowing this, that's my starting point. Is this vector equal to 0? What do you think? How can I convince you equal to 0? All right, to convince you equal to 0, I took x1 plus y1, to y2. And I start rearranging the terms because I want to use the fact that x and my starting vectors have their properties. So I arrange the term this way and rearrange, just play a little bit with the term. By doing this, I know that this is 0 because my starting vector is in H, and this is 0. It means this is equal to 0. So the first component of my new vector plus the 2 times the second component of my new vectors is equal to 0. Therefore, my new vector is in H. So that's the algebra behind it. Now again, close and the scalar multiplication. I start with an arbitrary vector in H. So what does it mean in H? It means I start with a vector that satisfies first component plus 2 times the second component equal to 0. And then I check, I multiply my new vector by a scalar and ask myself, is my new vector also in H? So I take C times X, I'm definitely creating a new one. Will this new one be in H? It means if I take the first component plus 2 times the second, will I get 0? Knowing that x1 plus 2x2 is 0. So I did that. Then I said, you know, I can factor the C, leaving me with x1 plus 2x2. But this one here, x1 plus 2x2 is 0 because my starting vector is not an arbitrary one. It's a very specific one. So x1 equal because x is in H, so Cx is in H, hence H is closed and the scalar multiplication. So H is a subspace. So every line through the origin is a subspace. Now, example number 4, suppose I take a line not through the origin, x1 plus 2x2 equal to 4. Is this a subspace? If a line does not go through the origin, this is not a subspace. It means I take all the vector where the tip is actually on this line. It means the x1, x2 satisfy this condition. It means those are the vector I'm thinking of. Then this is not a subspace because the 0 vector is not in it. Absolutely, it's not a subspace. Actually, nothing is satisfied. Even scalar multiplication is not satisfied because if I take a vector whose tip is right here and I stretch it, I stretch it. This new one is definitely not in H. So vector lines that don't go through the origin are not subspaces. All right, so one more properties, and then we characterize basically all the subspaces, but a simple property. If H is a subspace, it means H is specific thing. It's bunch of vectors that satisfy all the 3 properties. And X and Y's are in H. Then every linear combination of them will be also in H. Is this a correct statement? Does this statement make sense? What do you think? So I tell you yes, because if I tell you H is a subspace, I'm not talking about just anything. I'm talking about something very specific. I'm talking that H is a collection of vectors that have the property, if when you add two vectors from it, your new one will be in H, and you take any, so you start with a vector in H, you scale it, you stay in H. Very particular subset. So now I'm telling you that if H has this property, so if I start with any two vectors and I take a linear combination of them, this new one also will have to be in H, because if X is in H, scaling it will be in H. So that's really the idea. X is in H, you scale it, you don't leave H. Y is in H, scale it, you stay in H. Both are in H, adding them will keep you in H as well. So if H is subspace and X and Y are any two vector in it, then the linear combination is also in it. And this would lead me a little bit to study the subspaces of R2. What are the subspaces of R2? The only ones. There is nothing else, actually. The subspace that consists of the zero vector only. Doesn't T and S have to be greater than 0? No. No. Because when you have a subspace, then if a vector in it, every scalar multiple has to be in it, whether the scalar is positive or negative. So there is no restriction on the scalars. All right. Now, what are all the possible subspaces of R2? Because I want you to start building a picture in your mind of those subspaces. But I start with R2 and then I move to R3. Okay, the subspace that consists of the zero vector only. Is this a subspace? So if I tell you H contain only the zero vector, so H is just this point here. Is this a subspace? Of course. 0 is in it. Adding 0 to 0, you get 0. Times taking 0 times the scalar, you get 0. So the subspace that consists of the zero vector only. That's one of the subspace of R2. The second type of subspace is that every line through the origin is a subspace. And then all of R2 is a subspace. Of course, if you take all the possible vector x1, x2, all possible vectors, this is subspace. Adding two vectors with two components, you end up with a vector with two components. Multiplying a vector with two components with a scalar, you end up with a vector with two components. So all of R2. And the question, are there more subspaces than that? Is there anything else? And the answer is, do you think there is anything else? Actually, the answer is no. These are the only possible subspaces of R2. And let me a little bit give you an idea why these are the only subspaces of R2. There is nothing else. Because if suppose I start with a subspace, what's the picture? If I take a vector in it, if this is a subspace, the whole thing has to be in it. So if it has one vector, it has to have the whole line in it to be a subspace. So this line is a subspace. If it has two vectors in it, like this. So suppose this is U and this is V. Suppose V is in it. Then everything on this line has to be in H. Actually, that's interesting. Do you think those two lines form a subspace? Yes or no? Suppose I tell you H consists of those two lines, this one and this line. Will this be a subspace? I'll give you a minute to think about.
No, because if you added a vector from one of the lines to a vector of the other lines, it wouldn't land on one of the other lines.
You agree with him? I want chat. I want answer before I repeat what he said. Do you agree with him? Yes?
Yeah.
Yes? Absolutely. Absolutely. Those two lines cannot form a subspace because if you take something here and something here and you add them, you're absolutely not in H. So absolutely two lines like this do not form a subspace. But now this is the thing. If your H have U and V, Now my question to you is the following. Will this vector here be in H? So if those two vectors are in H is subspace. So will this vector that I picked arbitrarily will be in H also? What do you think? Yes or no? I want answers and justification. Who's ready? Okay, because we don't have a lot of time left, and the answer is yes. Once it has those two vectors, this vector W will have to be in it. Actually, any vector will have to be in it. And the reason is, this W, I can write it as a linear combination of my vector U and my vector V.
So would
Yes.
H be a part of that line in the origin, and then that line across the
So H will have to contain this line.
yeah.
H will have to contain this line.
Okay, so yeah, it would fit because it's
And it has to contain anything else, because if I take any vector W, I can write as a combination of a little bit of U and a little bit of V. What we've done at the beginning of the semester. So W will have to be in H. So once it has two vectors, which are basically nearly independent, H will have to be all of R2. So that's why the only subspaces we can have are the 0, line, and all of R2. Now the picture in R3, and I will finish. What are the subspaces of R3? Even though I did everything in R2, but the whole picture actually generalizes. In R3, the subspaces that consist of 0 vector is also a subspace. Every line in R3 through the origin is a subspace, which is actually make absolute sense, at least geometrically. Now, but there is one more addition in R3. Every plane through the origin is a subspace. Is this correct?
yeah.
We think geometrically. Take just a plane through the origin. Then taking a vector in this plane and stretching it, you will never leave the plane. Take two vectors within this plane, adding them, you will never leave the plane as well. So every plane through the origin is a subspace. All of R3 is a subspace. So that's the picture in R3. Okay. Now, the problem that I actually didn't have the chance to do is I'm stretching the ideas. I'm giving you more subspaces in R3 this time. I'm asking you also the question, is this a subspace? The technique to do it are verbatim what I've been doing for R2. And in your homework, you will have a little bit more of collection in R3, not only in R2, just to generalize. Okay, any questions, any complaint before? Is there any application of subspaces? Yes. I mean, a lot of the mathematical object you work with, which is something I'm gonna, one example will be next time, will be a subspace. And yeah, they are very important object in math, because they are objects that tells you that if two vectors have these properties, then their sum will have this property. And I will start with probably Tuesday and Thursday or next Tuesday by a real example that from linear algebra. All right, any other questions? How did the quiz go before I let you go? Did you guys have enough time? I want yes or no answers.
Yeah.
Yes,
Kind of.
great. Now I want you guys to be able, all of you, to download it into Blackboard, because it's really easy for me to be able to grade you in Blackboard. If you guys send me email, it's really a nightmare to do that. And Blackboard, I can immediately send you a comment. Email, I have to email you the comment. I would rather actually send you a comment through Blackboard. So please try this time just to email it to, send it to me through Blackboard. Even if you do it late, I don't really care. I want it through Blackboard. And if in the worst case scenario, you couldn't email it to me, but I really want it through Blackboard. I emailed it because I wasn't sure I could submit after time was up. I'm going to let you do that, but not 1 hour after time is up. I mean, 5 minutes. You will be all right. Okay?
Okay.
All right. Bye-bye, guys. I have to move to another classroom. Please remember, I have office hours from 12 to 1:30, and you have the URL for the office hours. Please join me if you have any questions. All right? Don't let it slide by. Don't let anything slide by. Bye-bye, guys.